Hello everyone, I'm Mala. I'm going to be your mentor for the group led by Sarah Cook, discussing her paper Factoring Gleason Polynomials Modulo 2. So, this pre talk is going to be a brief introduction to the Mandelbrot set, which is one of the focuses of Sarah's paper with both Floyd and Perry. Um, I think the knowledge I'm going to assume, the prerequisites I'm going to assume are just basic complex analysis at the undergrad or at the grad level. So let's get to it. Um, okay, so complex dynamics is generally the study of holomorphic functions defined on a Riemann surface or more generally on some complex manifold, a self map of a complex manifold. So for our purposes, the Riemann surface that we're going to be interested in is the Riemann sphere, and all holomorphic functions in the Riemann sphere are rational functions. So if you have a rational function, we care about its iterates, so f of f, and so on, and we care about changing the function and inputs for the function. So, but we don't need like a specific formula because of the following reason. If you have a rational function f and a Mobius transformation phi, then if you look at the function phi of f of phi inverse, that is, if you conjugate f by phi and then iterate that n times, that's the same as iterating f n times and then conjugating by phi. In other words, phi of f iterated n times of phi inverse. So this commutative property allows us to think of rational functions mostly up to Mobius conjugacy. So we can choose formulas for a function within its conjugacy class, if that makes sense. Um, so case in point, the simplest family of rational functions is the family of quadratic polynomials in terms of complexity. Um, every quadratic polynomial is Mobius conjugate to a unique polynomial of the form z square plus c. You can try this yourself. Like if you have a z square plus bz plus c, you can use some Mobius conjugation for this function to get it into the form z square plus c. You just have to move the critical point to 0 while keeping the other critical point at infinity. So for this polynomial f sub c, there is a unique critical point which is at 0, and the unique critical value is the point c. This is on the complex plane. And infinity is, of course, a critical point, and infinity is a fixed critical point. Okay. I said that we care about different inputs and outputs. So in particular, we will distinguish between the dynamical plane of FC, that's the Z plane. So that's the space of inputs, and the parameter plane of FC, which is the space of functions FC where C varies. So this is the C plane, the complex plane. Okay. What is the Mandelbrot set? The Mandelbrot set is a subset of the parameter plane. What is it? It's the set of points C where the orbit of 0 under FC is bounded. So you take the critical point of, you fix a C, you go into the dynamical plane of FC and you look at the critical point, which is 0, to look at what happens to that point under iteration. If it escapes to infinity, then C is not in the Mandelbrot set. If it doesn't escape to infinity, if this orbit stays bounded, then C is in the Mandelbrot set. Okay. So we know by work of Doherty and Hubbard several decades ago that the set M is connected. We also know that by the same work, we also know that it's compact. And its complement is simply connected, which I will mention later. So there is also a degree D generalization. If you look at the set of degree D polynomials with one critical point, everything of that form can be represented by z to the d plus c, where c is some complex number. And we define the degree D multiprod set to be the set of C such that the critical orbit of f sub C, f sub dc is again bounded. So all these polynomials have only one critical point, and we care about what happens to that critical point, and we want to distinguish the parameters themselves by whether the critical orbits escape or not. Okay. So Doherty-Hubbard's proof can also be applied to the multiplot set of degree D to show that it is also connected. So everything that's true for the Mandelbrot set is mostly true for the multiplot sets. Okay. So this is an image of the Mandelbrot set. As you can see, it seems to be simply connected. The complement is simply connected, and it seems to have several components, and you can show that it's a compact set. So yeah. Okay. So now, this is an object of interest. The Mandelbrot set is an object of interest in the parameter plane, but you can also look at the dynamical plane. And here are some things that we care about in the dynamical plane. So, if you fix a parameter c and a specific, therefore, if you fix a specific polynomial f sub c, some objects of interest that we care about are n periodic points and consequently n periodic cycles. What's an n periodic point? It's a point that comes back to itself under f sub c after exactly n steps. So that's an n periodic point. Um, and we also care about the cycle containing an n periodic point is called an n periodic cycle. We also care about the non-escaping set. So this is the set of points z in the complex plane for which the forward orbit does not go to infinity. The forward orbit is bounded. Um, so here's a deep theorem. It says that the non-escaping set of Fc, z square plus c, is connected if and only if the critical orbit is bounded. So, or in other words, C is inside the Mandelbrot set. So if C is inside the Mandelbrot set, the non-escaping set is connected. And it turns out that there is a nice dichotomy here. If you take a polynomial or a parameter C that's not inside the Mandelbrot set, then it turns out that the non-escaping set is actually a Cantor set. So I would like to show you some examples by running some code. So I have this software named Fractal Stream. That's Fractal Stream. And I'm going to show you some code that generates a Mandelbrot set. So this is a software that has its own scripting language, which I hope will be useful during the course of this semester. Um, what I have here is a picture of the Mandelbrot set. Every point here corresponds to, this is in the C plane, so every point here corresponds to some polynomial. Now, if I click on a point inside the Mandelbrot set, for example, this one, what you see highlighted in black is the non-escaping set. So it's a set of points whose orbits don't go to infinity. So if I click on something here, that's going to stay inside the set, inside the black set. If I click on anything outside, that's going to go to infinity. Okay. So this is for a polynomial that's inside the Mandelbrot set. If I choose a polynomial that's outside the Mandelbrot set, you'll see that the escaping set is now a Cantor set. So almost everything in the dynamical plane of this polynomial goes to infinity. And for these specific inputs that are in this Cantor set, which we can't even choose carefully because the zoom function isn't amazing, if you're able to pick a point inside this Cantor set, you'll actually see that it's going to stay inside that Cantor set. But we can't do it very accurately because computational reasons. So that is the dichotomy that's an alternative definition of the Mandelbrot set almost. You can define it as a set of C for which the non-escaping set of Fc is connected. Okay. Let me get back to my slides. So okay. So now, so that's about non-escaping sets. If you look at periodic cycles can behave differently based on certain invariants of that cycle. You can have cycles that attract points around them. That's an attracting cycle. You can have cycles that repel, that act as sources. They repel points around them. That's a repelling cycle. You can have other types of cycles and so on. So generally, what happens around a periodic cycle, the local dynamics around an n-periodic cycle depends on this number called the multiplier of the cycle. So given any cycle zeta of period n for a specific polynomial f sub c, we define the multiplier to be the derivative of f iterated n times at any point in the cycle. So of the first return map rather. So take any point z, for example z1 inside an periodic cycle. The first return map at z1 is just f iterated n times, fc iterated n times at z1. Look at its derivative, that's the multiplier. So the local dynamics around a periodic cycle varies depending on the value of the multiplier. So if this multiplier is inside the unit disk or its absolute value is less than 1, then the cycle behaves like an attracting cycle. It attracts points around it. This is all very vague, but you can find details in the references that I've listed here. this is not really like the particular analysis is a bit deep, and like I can't cover it in a 20-minute video, but I have hopefully the listed references help. So that's an attracting cycle. It's something with multiplier less than one, an absolute value. In particular, if the multiplier is zero, then we call that a super attracting cycle. If you think about it for a minute, multiplier is zero means that the derivative of the first return map at any point in the cycle is zero. But that also means that because we're looking at a polynomial, that also means that the cycle contains a critical point. Only then can the derivative vanish anywhere inside the cycle. So, um, so a super attracting cycle equivalently is a cycle containing a critical point of FC, or in other words, it's a cycle containing zero because FC has only one critical point on the plane. Okay. Um, you can also think of infinity as its own attracting, a super attracting cycle. So infinity is a fixed point for the function f sub c. And if you look at, since it's a critical point, if you look at under some suitable change of coordinates near infinity, you can actually compute the derivative of f sub c at infinity to be equal to zero. So for example, if you look at the function 1 over z, if you conjugate f by 1 over z and look at that thing near infinity, then you can compute the derivative at infinity to be equal to zero. Therefore, infinity is a super attracting one cycle. Okay. You will also have things called parabolic cycles, which are cycles where the multiplier is a root of unity. And lastly, the complement of all these, that is, when the multiplier is not a root of unity, but it has absolute value 1, is an indifferent cycle. There are different types of indifferent cycles, but that's outside the scope of this talk and this semester. So uh, please look at the references if you would like some details on that. But yeah. So, what's special? We particularly care about attracting and parabolic cycles in the semester. What's special about these cycles is that they always attract the orbit of some of the critical point or the critical value. So, if you look at the neighborhood of any attracting cycle, you'll see that the orbit of zero, which contains C, eventually like gets closer and closer to that. And similar things happen for periodic cycles. I'd like to show you an example. So, um, let me go back to my fractal stream code. So here's the Mandelbrot set. I'm going to take a polynomial which you should take my word for it right now. This polynomial has an attracting cycle. If so, this point right here is, you can see on the top. So you can see in this box what point I'm at right now. So this is in the dynamical plane of some polynomial, quadratic polynomial, and zero, this point, it's the critical point. Now under iteration, you see that zero slowly approaches this thing that looks like a 3 cycle. So this 3 cycle is an attracting 3 cycle. And the same thing is also true for parabolic cycles. It's just that a parabolic cycle doesn't attract everything around it, whereas an attracting cycle does. But that distinction it requires more detail to spell out. Okay. Um, and because, okay, so I just said that if you have any attracting or parabolic cycle, it attracts the critical orbit. As a consequence, since there is only one critical orbit, you can have at most one cycle that's attracting or periodic. So that's a very strict property that's true only for these polynomials z square plus c, and in general z to the d plus c. Since you have only one critical orbit, you can have at most one attracting or parabolic cycle, and it's possible that you don't have any attracting or parabolic cycles on the complex plane. So yeah, this is all in the complex plane. Of course, infinity, the point at infinity is always super attracting. So barring that, you can have at most one cycle that's attracting or parabolic. Okay. Um, so one of the focuses of Sarah's paper are these points called centers. These are going to be the roots of what she calls the Gleason polynomials, but we will introduce them from a different point of view. A center of period n is a point in the complex plane for that corresponding polynomial, 0 is n periodic. Okay, so you take f sub c, you want f sub c of iterated n times at c to be equal to c. This is equivalent to saying f sub c iterated n times at 0 is equal to 0. So calling the critical point periodic of period n and calling the critical value periodic of period n are equivalent. Um, so that's a center. and tautologically, all centers have to belong to the Mandelbrot set because the critical orbit is a periodic cycle. It's not even just bounded. I mean, it is obviously bounded. So yeah. So here is an example. The point C equal to 1 is a center of period 2. Why is that? We note that under f sub minus 1, which is the polynomial z square minus 1, the input minus 1 goes to 0, and then 0 comes back to minus 1. So minus 1 and 0 and form a 2 cycle. So that makes C equal to minus 1 a center of period 2. It turns out that all centers are contained in the interior of the Mandelbrot set. Um, so a connected component of the interior of the Mandelbrot set, which contains a center, is called a hyperbolic component. So which are going to be one of the main players during our semester. So I can show you a picture in a minute. So in this picture, you'll see, first of all, this is a reproduced image of the Mandelbrot set. All the dotted points, the pixelated points that are colored, highlighted brightly, are all centers. So the white point right in the middle here, this is the point C equal to 0. So this is the polynomial z square. This is a center of period 1. This is C equal to minus 1, which we just discussed. This is a center of period 2. This is a center of period 4. This is a center of period 3, and so on and so forth. If you zoom in here, you'll see a lot more centers, but I'm not quite sure of the resolution of this picture, so I'm not going to do that. Okay. Let me go back to my slide. So that's a hyperbolic component. Oh yeah, in this picture, I suppose. So this component that contains the point 0 is an example of a hyperbolic component because it is a component of the interior of M that contains the point 0. Of course, I haven't proved that it is, but I just want to indicate it to you. Okay. Um, okay. Um, but then we also have, so that's a hyperbolic component. It's a component of M that contains a center. But we can also make sense of define a notion of hyperbolic polynomials in the following way. So a polynomial is hyperbolic if the critical orbit, which is the orbit of 0, or equivalently, or the orbit of C, um, tends to an attracting cycle. If so, a hyperbolic polynomial is basically something that has an attracting cycle. Because we previously stated that any attracting cycle attracts the critical orbit. Okay. So all hyperbolic components are of the following three categories. So it's possible that C is a center of period n, in which case we saw that if C is a center of period n, then the cycle containing C necessarily has to contain the critical point also. Therefore, the cycle, if C is a center of period n, then that F sub C has a super attracting cycle, which is basically the cycle containing C. So in other words, the point C belongs to a super attracting cycle, and therefore F sub C is a hyperbolic polynomial. Similarly, if C is outside the Mandelbrot set, then F sub C tends to infinity, which is a super attracting fixed point. Therefore, any such F sub C is also a hyperbolic polynomial. The last category is that if C belongs to a component of the interior of M that contains a center. So in other words, what we called a hyperbolic component, then what we can show is, okay, if C is in a, if the center has period n, then, and C belongs to the same component as the center, then FC will have a cycle that's attracting of period n, if that makes sense. I will show you an example in a minute. Let me go back to fractal stream. So I said that this component, the biggest bubble that you see right here, is a component of period 1. So this is the point 0. This is z square. So if I look at its dynamics, I see that 0 is a fixed point, and then everything inside this black set tends to this fixed point. So 0 is a super attracting fixed point. If I look at any other polynomial inside this component, for example, this one, now 0 is now somewhere here. And then you'll see that 0 is no longer fixed, but it's still tending towards a fixed point. So this fixed point is an attracting cycle of period 1. In fact, if you choose any polynomial inside this big cardioid, if I pick something here, the same thing will happen. 0 is eventually going to converge to some fixed point that functions as an attracting fixed point. Okay. And the same thing is true if I go into this bulb, for instance, at the center of this bulb, which is -1, which happens to be -1, we'll see that 0 is in a 2 cycle. 0 maps to -1, -1 comes back to 0. But then if I change the polynomial to something else within that component, then 0 will no longer be 2 periodic, but 0 will tend to something that's 2 periodic. So everything in a hyperbolic component, for every polynomial in a hyperbolic component, there is an attracting cycle of the same period, and the critical point is eventually attracted to that cycle. So that's the idea. Okay, we'll see a little more about the structure of these hyperbolic components, but there is this really big conjecture that says that hyperbolic components are actually dense inside the Mandelbrot set. It's not been proven yet. It's been the conjecture was posed, I think, like several decades ago. It's still open. So yeah, we already saw some pictures of hyperbolic components. All the centers here are highlighted bright in colored pixels, and the components containing these centers, which you can maybe visualize, are the hyperbolic components of that specific period. Okay. So you can alternatively think of a hyperbolic component in the following way. So take the set of all polynomials for which the critical orbit tends to an attracting n cycle. Take a connected component of this set of polynomials. That's exactly what a hyperbolic component of period n is. So it's just a bunch of polynomials that live in some connected set, all of which have an attracting cycle of the same period. That's it. Okay. So I'm going to describe further the additional structure of hyperbolic components. We saw that every hyperbolic component contains a center. What is true is, in fact, that every hyperbolic component contains a unique center. Now, why is that? So let H C naught be a hyperbolic component that contains a center C naught of period n. So the center and the component all have period n. Now, for any polynomial inside this component, let zeta sub c be the corresponding attracting cycle, which also has period n under that under fc not fc. So what I'm doing is I'm going back to this picture. If you start with the biggest bubble that you see here, the component containing 0, pick any point in this component and call its corresponding fixed point zeta sub c. Okay. Then you can compute the corresponding multiplier of that specific cycle, that specific attracting cycle of period n. So you have a canonical multiplier map from um, this hyperbolic component to the complex plane. It's just defined as take C for fc, take the cycle zeta sub c, look at its multiplier lambda sub c. So this multiplier map actually, because all these cycles are attracting, by definition of the multiplier, lambda maps this component into the unit disk. But what is true, in fact, is that lambda is a biholomorphism from H to the unit disk. So this is basically saying that every hyperbolic component is a disk, and the canonical biholomorphism is the multiplier map. So the inverse function, lambda inverse, from the unit disk to H sub C naught, actually extends as a homeomorphism of the closed unit disk onto the closure of C naught. So you can extend the inverse map from to the unit disk, and the extension is a homeomorphism. So this gives you a different way of thinking about the center and some other points in the hyperbolic component. Now, what is the center? It's because this multiplier map is a biholomorphism, there is a unique point in the component which has multiplier under which the image of the multiplier map is 0. So you can think of the center as the pre-image of 0 under the multiplier map. So the center is the unique polynomial inside my component which has a super attracting cycle of period n. You can also define the boundary of the hyperbolic component in this way. You can look at lambda inverse of S1. Now, what's in this boundary? If you look at any polynomial corresponding to a boundary point, then that polynomial will have it'll have a cycle with multiplier in the unit circle. So that's a parabolic or an indifferent cycle. So the boundary of a hyperbolic component consists of polynomials that have either a parabolic or an indifferent cycle. So the problem is the following. If you have a parabolic cycle, then in general its period only divides and it doesn't necessarily have to be equal to n. So Let me show you an illustration. Let me get back to fractal stream. So I'm going to start inside this big cardioid. If you look at the dynamics, actually, everything in the cardioid has period one. So let me start with the different component. If I look at the dynamics of this thing right here, I'll see that 0 eventually tends to a 2 cycle. So this is a hyperbolic polynomial of period 2. If I look at this one right here, again 0 tends to a 2 cycle. If I look at something closer to this, again 0 tends to a 2 cycle. If I look at something closer here, this cusp right here, again 0 tends to a 2 cycle. But you'll see that under iteration, the points in the 2 cycle are actually getting closer and closer together. Like the orbit of 0, it goes like this, but then the points in this orbit are getting closer and closer together. So they're actually all tending towards a 2 cycle that's getting closer and closer to a point of this form. So if I move all the way to this point right here, which is not very accurate because computational deficiency. So this point right here, that point that adjoins these two hyperbolic components, is in the boundary of the smaller one. So it's not inside, it's not in the interior of the component, it's on the boundary of this component. Now, if I click this point and look at its corresponding input plane, if I look at the orbit of 0, you'll see that its forward iterates are getting closer and closer together. So the orbit of 0 doesn't tend to a 2 cycle, it actually tends to a 1 cycle. And this 1 cycle is a parabolic cycle, it so happens. So what can happen is that as you move around in your hyperbolic component, you have attracting cycles of period n, but as you tend towards the boundary, these cycles could degenerate into a cycle of smaller period and become a parabolic cycle of smaller period. That's exactly what's happening here. So we care about one particular point on the boundary of the hyperbolic component. What we can do is we can look at this multiplier map. Because the inverse extends to the closed unit disk, there is a unique point C1, which is lambda inverse 1. We call this point the root of the hyperbolic component. So if I go back to fractal stream, now for this component right here, if you can see my cursor, this point right here is the root. This is the unique point for which there is a parabolic cycle. And for the multiplier map of this component, this is the point which is the preimage of 1. So every component has a root, and the problem is because we have all these degeneracies, what could happen is the following. So if I look at the dynamical plane of C1, all I know is that I have a parabolic cycle of period that divides n. The period doesn't necessarily have to equal n. As a consequence, what could happen is that the multiplier of the cycle could be equal to 1, or it could be just a root of unity. Some power of the multiplier of the cycle could be equal to 1. So if the multiplier of the cycle is equal to 1, then HC naught is called a primitive component. Otherwise, HC naught is called a satellite component. Another way to think about this is that a primitive hyperbolic component is one in which these attracting cycles, as you tend towards the root, don't degenerate into a smaller period cycle. The parabolic cycle is of the same period as the period of the component. That's a primitive component. A satellite component is of the opposite category. If you move around in the component towards the root, then the attracting cycles of period n um, collapse into a parabolic cycle of smaller period as you tend towards the root. So we make a distinction between primitive and satellite components, and there's actually a very visual difference between the two types. So what I've done here, I've zoomed into two different components of the Mandelbrot set. One of them is it's like if you zoom into this region of the Mandelbrot set, you'll see the smaller copy of the Mandelbrot set, and the red region, the red curve is the boundary of a specific hyperbolic component. This component is called a primitive, and you'll see that it's not attached to any other bigger component. This point right here, the cusp point right here, is the root of this component, and C naught is the center of this component. Um, On the other hand, if you look at this bulb over here and zoom that in, that's an example again of a hyperbolic component. This point C naught is its center. This one, as it turns out, is a component of period 2. And if I go towards its boundary and look at this point, I'll see that that point has a periodic, a parabolic cycle of period 1. It's not a period 3 anymore. So the distinction between satellite and primitive components is that primitive components are sort of detached. Satellite components are attached to bigger hyperbolic components. So this component is attached to the bigger one. The root is a cut point between them. So this is a basic introduction to primitive and satellite components. But in the course of the semester, perhaps I can show you more illustrations to look at the difference between the two. Okay. We also care about what's called external rays. So previously I stated that the complement of the Mandelbrot set is actually biholomorphic to that's also simply connected on the sphere. So the exact statement is if you look at the complement of the Mandelbrot set in the plane, that's biholomorphic to the complement of the closed unit disk in the plane. So everything outside the Mandelbrot set you can think of as the outside of the unit disk. And the biholomorphism in question, which we call phi sub m, is actually asymptotically the identity. So near infinity, it looks like the identity. Um, this means the following thing. This gives rise to what are called external rays. What you can do is you can visualize the exterior of the Mandelbrot set, especially near infinity, as the exterior of the unit disk. And you can think of pre-images of radial lines emanating from infinity under this biholomorphism. So what you do is you fix at an angle theta in Armogy, and you look at the external ray. You define the external ray of M at angle theta to be everything that maps to the ray at angle theta coming from infinity under this biholomorphism phi sub m. I think a visualization would be good. So think of so if my angle theta is 1 over 3, for instance, I'm looking at the radial line of the form r e to the power 2 pi I times 1 over 3. So 2 pi I times 1 over 3 near infinity, it's coming in from this direction. So asymptotically for the Mandelbrot set, it's also coming from this direction. But if you go towards the Mandelbrot set, then the line starts bending. So that's an external ray. So you're just looking at the image of radial lines from infinity uh, under the pre-image of radial lines from infinity under this map phi sub m. And if you fix a specific ray at a specific angle, then that pre-image is called an external ray to the Mandelbrot set at that angle theta. So here are some external rays that I've indicated here. So this is a ray at angle 1/3, ray at angle 2/3, 3/7, 4/7, and so on. There is a ray at angle 0 that lands right here. And I only care about rays angles modulo 2 pi. So I can look at them as elements of Armod G and so on. So um, again, if you look at the multibrot set, that is the Mandelbrot set for Z to the D plus C, you can make a generalization of hyperbolic components, external ray centers, and everything that we have stated here. So this is like some basic material for Sarah's talk and the semester. This picture, by the way, is from Sarah's paper. You can look at it there, and there's the same description of external rays. Um, so general references for this pre-talk, for Sarah's talk, and generally for the semester are Doherty and Hubbard's book. Notes actually called the Orsay Notes from 2009. You can find it PDF immediately online. Standard reference for complex dynamics, another one is Milner, his book Dynamics in One Complex Variable. This is also easily available online. Hubbard also has a book on Tag-Miller theory and its applications. So the volume 2 of this book has two chapters, chapter 9 and 10, which focus on complex dynamics. And specifically, they talk about properties of the Mandelbrot centers and so on and so forth. So that's a very good reference. I think there's a version that you can download from MathSciNet if you have access. Otherwise, I assume that most of you are attached to a university. I think you can find it very easily in the library. If anybody needs help accessing this textbook, you can let me know. And yeah, the other reference is just Sarah's paper. At some point in the semester, I might if you're interested, I can tell you how Fractal Stream works and how to download it and use it and so on. There's also other software if you don't use a Mac. So Let me stop here. I hope this talk was useful. Thank you.